I hope you are able to see the screen.
Yes, sir.
So how will you measure the resolution of the dynamic comparator? Remember, it is a clock driven comparator, right? So in the dynamic comparator, it is working with a preset or a pre-charge. So you have the inputs. So VREF is there, VIN is there, but there is one clock input and then there is a preset input. So the operation point of view, anybody can suggest how will you check the resolution? Static comparator is a different thing. Whatever he mentioned was correct because the static comparator, which is not driven by a clock, we saw that ultimately for static comparator, so we have a transfer characteristics. Suppose positive input to positive output, you are looking at it. So at some point it goes steeply up, and then So this basically this transition region determines what is that smallest delta V for which it will cross. Of course, your reference is fixed at a particular point. So this is your V out versus V in, and your reference is somewhere maybe here. Reference maybe somewhere middle here. So this is your VREF. So the moment V in crosses VREF, V out goes to high, and there is a transition region over here. So the width of the transition region tells you that for what minimum difference the comparator will switch the state, right? So output will switch from 0 to 1 or 1 to 0 for what minimum difference. That is the minimum difference it can resolve. But for dynamic comparator, what will you do? Dynamic comparator doesn't have this.
So one thing which we can do is that we can ramp the voltages in between the clock cycles. That there is when the clock is off, that is it is already pre-charged. The pre-charging PMOSes are off, and in during that duration we can steadily ramp up the voltage, and then we can check that at which point the comparator transitions. Then again it goes preset after the next clock.
No, so you have to. It's not that for different phases you have to do this. You have to do it for the normal operation of the comparator where the pre-charging, discharging is going on. So initially, this is for static comparator, applicable to only static comparator, for only static. This is your dynamic comparator. Now for that, the waveform is you have a clock. And during when you're ramping the signal, so your input signal is being ramped. V in, and you have some VREF, so VREF is somewhere here. This is time axis, and this is your clock. So now for the time above this crossing point or before this crossing point and time after the crossing point, results should be different, right? Because ultimately you are changing the state, means the results for these two cases should be different. So at this point, it will basically try to switch. Ideally, what we should expect is the result just before this and after this point should be different. So if I assume that my clock edge is coming here and the active edge is where it evaluates, suppose active edge is coming here. So now what will be the output waveform looking like? V out. Now, as long as V in is less than VREF, V out should be discharged to 0 all the time. So every negative cycle, the V out is getting pre-charged, and then after that, it is getting discharged to ground. Again, recharged, and then when the evaluation time comes, discharged to ground. that is going to repeat. Precharge, why I'm drawing faster? Because precharge happens slightly faster because you are just having the PMOS directly charging both the output nodes. Discharge takes some time to settle. So intentionally, I'm drawing the discharge phase a little bit sluggish. This will keep on repeating till this point. So again, I think I made a mistake because here it was supposed to go high and here so I made a mistake in drawing. So anyway, I will have to delete this and draw again. Or I could have drawn it on the top of the clock so that the matching problem is not there. So let me just select this entire thing and delete and then draw again. So precharge phase is when clock equal to 0. The way we have drawn the NMOS input device comparator, when the clock is 0, the precharge will be happening. And then again, when the evaluation phase comes, it will go down. And again, when the precharge comes here, again, it will go up. And then again, the evaluation time, it will go down. So this one will keep on happening. Again, it will go up. And then the evaluation time comes when the clock goes high. Again, it will go down. Right. So this is happening. Precharge phase it goes up, evaluation phase it goes down. Again, precharge phase it goes up. But now, when the evaluation has come, what should happen here? This evaluation phase, the as VIN has crossed the VREF. VIN has become bigger than VREF. Therefore, it should remain high, right? It should remain high. And then only in the next evaluation recharge phase, again, it will remain high, right? After that, again, you are going to get clock high. Again, it is going to evaluate. Again, it is going to remain high. After that, all throughout, you will see that it is remaining high. Is it what we are going to expect? Is it clear to everyone?
Yes, sir.
So because in the precharge phase, anyway, it goes to high. Output goes to high. Both output goes to high. But in the evaluation phase, it will go low because the VIN is lower than VREF. But after the VIN has crossed VREF, it will remain high. And precharge phase, anyway, it is remaining high. So all throughout, it will remain high. A little bit of glitch will come, but it will remain high. So now, here, if you want to see that what is the resolution, we need to see exactly for what difference it is changing the state. And for that, we may have to play with the slope of the input signal. That means if we can ramp the slope such that within one cycle, the slope is changing by 1 millivolt or it is changing by 0.1 millivolt. Suppose, the change from this cycle, the previous evaluation cycle to this evaluation cycle is hardly 1 millivolt. Suppose this difference that we are getting is 1 millivolt. And for that 1 millivolt, it is able to change the state. Then we can say that it is reliably able to resolve 1 millivolt difference. Right? If it is 0.1 millivolt, that even for 0.1 millivolt difference, it is correctly able to evaluate. For all cycles above this, for all cycles before this, crossing point, it was completely remaining 0. And above this crossing point, it was completely remaining 1. Then we can say that it is able to resolve 0.1 millivolt. So the way to determine the resolution in the dynamic comparator will be to adjust the slope so that within one clock cycle, you are having a delta V increment. Whatever resolution you want to check that, okay, whether it is able to resolve 1 millivolt or not. So I will make sure that from cycle to cycle, the ramp is changing by 1 millivolt. If you want to evaluate whether it is able to detect 0.1 millivolt difference or not, then you will make sure that from cycle to cycle, that means in one clock cycle, the ramp is changing by 0.1 millivolt and try to see whether from one cycle to another cycle at the crossing point, it is able to evaluate correctly. That means for all the phases before the crossing point, it should be 0. After the crossing point, it should be 1. And it should be able to resolve the difference. So you have to adjust the slope. Because here there is no continuous characteristic. It is not like a static comparator where you can get the slope of the transition characteristics. Is that understandable for everyone? For static comparator, you
Yes,
can
sir.
do this. So I think I had given some assignment on static comparator also before this. Did
No,
I?
sir. Static comparator assignment was not given.
Static comparator, I did not give any assignment. Okay, maybe I missed it. Static comparator, anyway, we have discussed this, that your whatever op-amp you have designed, open loop operation, you can work that. You can make that also work as a comparator. So the dynamic one, if you have to get the resolution, this is the approach. And speed point of view, how will you check whether the speed is correct or not? In this case, how will you identify that the speed is coming? What are possible ways of checking what is the speed? At what speed it is able to operate?
Sir, by checking the clock frequency.
Clock frequency, yes. So checking the clock
Sir,
frequency
if
means what?
we,
What will you observe?
Sir, if we consider the here as you have written 0.1 millivolt. So if the slope is constant for the damping voltage, then by counting the number of clock pulses in between the intersection of the VREF increasing and the V in
No,
that we
no,
are.
that is not the speed. Because speed means whether it is able to resolve the output within one clock cycle. It is able to settle to the final value within one clock cycle. This speed cannot be compared, or speed cannot be evaluated over multiple clock cycles. If we have to see whether the dynamic comparator is working with a particular speed or not, all we need to do is to apply a small difference in the voltage. Suppose you determine the resolution. Resolution is suppose 1 millivolt. Now you apply that 1 millivolt difference and try to apply clock frequency, suppose 1 gigahertz. Now, at 1 gigahertz, you see that it is able to settle. It is able to evaluate correctly within that 0.5 nanosecond duration, because checking the speed, how will you check? So now if it is 1 gigahertz clock, my pulse width is 0.5 nanosecond. This is 0.5 nanosecond ideally. This is also 0.5 nanosecond. And your difference between the two signals you have applied, Vref and V in delta V, which is equal to say 1 millivolt. Now, within this 0.5 millisecond, what is going to happen? Sorry, 0.5 nanosecond, what is going to happen? Before beginning of every cycle, here the output will be precharged. So this is your precharge. And after that, within the 0.5 nanosecond, if Vref is V in is greater than Vref, anyway it will remain high. So there it is supposed to remain high. So there is going to be a downward trend, because you know that both the nodes start discharging in the beginning, and then finally it goes back to high. If the V in is greater than Vref, it should go back to high, depending on the polarity, how you define the V in and V out plus. So I'm defining the V out plus such that if V in is greater than Vref, V out plus should be high. That means the opposite side, right? Whatever branch you are connecting the V in plus, the opposite side output branch will be the V out. If that is the case, then if V in is greater than Vref, V out will be initially when the evaluation phase starts. This is the pre-charge, right? This is the pre-charge phase, and this is the evaluation phase. So during the evaluation phase, initially both the outputs start going down, but then depending upon the input conditions, one of them climb up. So remember that both the outputs initially they are pre-charged, right? Black one represents say V out minus, sorry, V out plus, and green one is V out minus. So both of them pre-charged to 1. Initially, both of them start going down, but depending upon the input, one of them will end up going down, another one will end up going up. When you observe the two outputs, it will look like this, right? All of you have seen this?
Yes.
Yes,
Now,
sir.
if that is the scenario, second case, if V in is less than Vref, ideally what we will expect just the opposite. So this is your V out, and in this case, this should go down. Whereas V out minus after a glitch, it should come up. This is what we are expecting. This is your V out minus, and this is your V out plus. This is your V out plus. So now, again, it will in the next cycle, what will happen the moment the lower phase comes, both of them will get recharged. Right? And then it will continue like this every cycle for this condition. Now, what happens if your comparator is too slow, or basically it needs more settling time? Slow means what? It can resolve the given difference of say 1 millivolt, but it needs more time to evaluate. So in that case, what will happen? So in this case, when the V out is supposed to go low, for the slow case, what will happen? V out may not be able to completely go down. It will be something like this, and then it will be pre-charge. So it may not be able to settle down to the minimum value. As you go on increasing, there is a slow case. That means it is not getting enough time to completely discharge to ground. Two outputs are getting pre-charged, but it needs more time to settle down. Even before it settled to the zero, it is pulled up and pre-charged because it's not getting enough evaluation time. T eval is greater than your, or basically less than the transition delay, or you can say the switching speed of the comparator. I can say T eval is less than T switch. T eval means the evaluation time you are giving to the comparator, and T switch means it will take to switch, actually the transition time required for the comparator to switch. So if you make it too fast, if you apply too fast clock pulses, you will see behavior like this. It is not able to go down completely. So when you see that, okay, after a certain clock speed, eventually it will start, it will fail to basically evaluate correctly. It will not be able to discharge completely. Both the sides will, the side which is supposed to go down will not be able to go down completely. Or it may also start giving erroneous results. So mainly this is the way we check the speed for dynamic case. The discharge path, the output which is supposed to go down fails to go down because it needs more settling time. If the speed is too low, if the clock speed is too high, this is what is going to happen. So at that time, we say that, okay, beyond this clock speed, it will not work. Is that clear to everyone?
Yes,
So you may say that the resolution is 1 millivolt. So that means that there you have not taken into account the speed, because for generating this particular plot, or basically resolution, we have not taken into account maybe the speed so much. This you can even have a clock speed of 1 megahertz and you can get a 0.1 millivolt resolution. But then for that 0.1 millivolt, remember that the lower is the difference between the two inputs, the smaller is the small signal current produced. Remember the comparator structure, right? So like a differential amplifier, it is having two input devices, it is producing the delta I between the two branches. So if the input signal itself is very less, that means the difference between the two input is very less, the delta I produced will be very less, and it will not be able to settle within a given time. So we can say that the difference that it is able to resolve at very low speed clock will be smaller. And as you go on increasing the speed, it will not be able to resolve that small difference. So again, the resolution has a trade-off with the speed. If you operate it at a very slow speed, it will give you the close to the best case reference resolution. That means, if you're going for low speed operation, best case resolution. As you go on increasing the speed, increase the speed. It will go down because the minimum difference it can resolve within that time will go down. Why? Because the small signal current is going down. If you have to check whether at 1 gigahertz clock is it able to resolve that 1 millivolt difference, you need to simulate with that 1 millivolt difference and check whether at 1 gigahertz clock it is able to perform properly. That way we can estimate first what is the best case resolution. For that, we can give a low frequency clock and a very small, very slowly increasing ramp, so that in one clock cycle it increases only a small amount. And with that small amount, delta V, we can check whether that delta V is getting resolved. So whether it is 1 millivolt, 0.5 millivolt, 0.1 millivolt. So we have to check that way. And likewise, the speed point of view, this is the way to check the speed. That once we have checked the best case resolution at low speed clock, now at different speed, as we go on increasing the clock speed, what is the difference between the two inputs that it is able to correctly resolve? Is that clear to all of you? Any question on this?
Yes, sir.
And as we have seen that the role of preamplifier should be increasing the resolution, because it is enhancing the difference between the signal which is going to the comparator. So if you use preamplifier, it should be gradually improving. Any question?
Sir, which point are you taking as the resolution?
Sorry,
Sir, which point, like which up and down slope?
what up and down
Like
slope?
which pulse are you taking as the resolution? The last pulse or the last pulse?
Your question is not clear. Can you speak a little louder?
Sir, the last pulse or the last pulse?
I don't know. Your voice, first of all, volume is too low, and I'm not able to, last pulse, last pulse. I'm not sure what you are asking. You can maybe type your question. Others are able to hear him clearly, because I see that the volume is too low. Yes. Corresponding to which pulse? So I told you, right? So there is no pulse with respect to which you have to take. You have to just make sure that the target resolution you're checking for, if you're trying to check whether it is resolving 1 millivolt or not, you need to make sure that within one period it is changing by 1 millivolt. The slope is ramping by 1 millivolt in one period. And then you just have to check whether, before and after the crossover point, it is able to switch from high to low. Is that clear? Yes, is that clear? You have to ramp the slope such that it is changing by the target resolution. If you want to check it for 1 millivolt, you have to ramp the slope such that it changes by 1 millivolt in one period. And then that's like the cycle at which that crossover point is coming. Before and after that, it should switch. If it is switching correctly, that means it is able to resolve that. And all the cycles after that switching point should be high. All the cycles below that switching point should be low. Is that clear? Yes, hello?
Yes, sir.
And there may be some circuit noise also. You may have generally, if the comparator has to compare very small voltages, then we need to make sure that it is very noise resistant also. Supply noise will be there, even if there is 0.1 millivolt of supply noise. What is the effect of that on the comparator resolution? So if you give a noise, say sinusoid noise, high frequency, it may also corrupt the resolution. So ultimately, if you have to get a very high resolution comparator, we need to make sure that the supply is also very, very clean. There is no noise external to the comparator. Likewise, the devices are also not contributing to much noise. Any other noise that is present within the or close to the comparator circuit, clock signal, any digital signal, any capacitive coupling with any other high-speed signal, all that can corrupt the comparator result, especially if you're going for very high resolution comparator. Is that clear to everyone? Any question on this? I hope now you will be able to complete whatever I had mentioned in the assignment. Any question regarding that? Static comparator, we have to compare the resolution that slope method, whatever we have discussed in the last class, that will work. This, the slope of this transition region, this you have to check. And then again, here also, as we have mentioned, this is the best case resolution. That means at low speed, this is the resolution you get. But if the signal itself is changing very fast, then you may not be able to resolve this fast. So if the signal is changing at a very high frequency, then comparator will not be able to resolve. It will not be able to settle to completely high or completely low value. Is that clear? Yes, any question before
Yes,
we
sir.
proceed?
Sir,
Everybody has the, yes, any question?
I have a doubt, sir. It's like on the assigned videos, sir. Like in that, you used a capacitor and current source to generate a linearly increasing reference voltage. And a counter was used to keep watch on time, and based on that, we got the digitally converted form of the analog input. So, sir, my doubt is, can we use instead a digital to analog converter, which could generate the reference voltage from the binary bit taking from the comparator?
So there are different ADC topology, right? So there is a SAR ADC which does that kind of thing, binary search algorithm. So there we use a DAC to convert the present digital output to analog reference. That's what you're talking about?
Yes, sir.
That is a different topology. Here it is a single slope ADC.
So, sir, can you tell how this one, the capacitor and current source one, is better in than that one, or like what are the benefits of this one, this topology?
We have not covered other topology, right? So right now I have not discussed SAR ADC or any other ADC. So right now, if I just discuss the benefit, I have to first explain what is SAR ADC.
Okay, sir. Thank you.
Any other question? Yes, any other question by anyone? So one thing that you also need to look at is how will you, right now the output is coming 0 or 1. So, but there is in this dynamic comparator, there is also the pre-charge phase. So the output is definitely, as we mentioned, every pre-charge cycle, it will be, pre-charged. So this is the clock, output will be pre-charged and then discharged. Again, depending on the input, it will be pre-charged and then discharged. So, and if the, if the opposite condition is there, that Vin is higher than Vref, then it will remain high. So here, till this point, I'm saying that, okay, Vref is here and the Vin is till this point is low. After that point, it goes up. So this is your V in, this is your V ref, this is your V out, this is your clock. So everybody is clear that this is that the output is going to look like V out. This is your V out. Is this clear? Yes. Is this clear?
Yes, sir.
Yes, sir.
So how will you now for digital circuits, or basically the comparator result is coming either 1 or 0. After this, I want to get a fixed output, right? So it should not be pre-charged every time. So how will you, what will you do after this point? Because here it is getting pre-charged and then conditionally discharged, pre-charged and conditionally discharged. So if I know that it is supposed to be discharged, my desired output is coming in this phase only. This is the output. This is the output. This is the output. This is not the output, right? This is not the output. This is not the output. This is not the output. So what will you do to get the, only the desired output pass to the next stage?
Use
Are you
an
getting
AND
the
gate,
point?
sir.
The pre-charge is, sorry?
Use an AND gate V out and clock.
AND gate, V out and clock.
Yes,
So
sir.
that is, not the best solution.
So we can have
Because
a
and again,
latch at
V
the
out in clock
output.
is,
So we can use a
sorry,
latch. A latch.
what kind of latch?
So we can use a D flip-flop kind of.
How will you use the D flip-flop? What will be the control of the D flip-flop?
So the comparator output will act as a, we can then use
What
a
will be the
negative
The
clock
edge.
to the
negative
D
edge of the
flip-flop?
clock. The negative edge of the clock.
Negative edge of the clock. So negative edge of the clock. So in the flip-flop, there is something called setup and hold time. Have you studied setup and hold time? I think in the lecture I have described that setup and hold time.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, hello.
Yes, sir.
So if I
Yes, sir.
use flip-flop, so what I'm assuming is that at the negative edge you are using a flip-flop, and because just after this negative edge it is pre-charged, just before this negative edge your desired input is available. So just before this negative edge my desired output level is available. Just before this negative edge my desired output level is available. If I assume ideal behavior, then the answer is correct. Yes, you can use a flip-flop with the negative edge triggered, so that at this stage, just before this transition, whatever output is available, it is going to register that, right? So in this case, the flip-flop waveform will, if you use a flip-flop, its waveform will be triggering at the negative edge. At the negative edge here, what will be the situation just after this negative edge? Yes, just after this is the negative edge, right? So just after this negative edge, what is the output of the flip-flop?
The low.
Sorry,
So the output
just
will be low.
low, right? Because just before this negative edge of the clock, just before this, the output is low here. So therefore, ideally, the output should remain low. Here also, second negative edge is coming. So till this point, also, if I see, if I assume that at this point, just before this point, this is the output just before this point. So here also should remain low. Only after this point, it will go high. So that is assuming that it is able to latch the output just before the falling edge. But then there is something called setup and hold time. What is setup time? Setup time. Full form
So
setup
minimum
time.
amount. So minimum amount of time the input signal should remain stable before the active edge of the clock.
Yes. So that is setup time just before the active edge of the clock. How much time the signal should remain stable? So is that a problem here? Setup time, is it having a problem here? Setup time? Just before the activity of the clock, the data is stable, right? It is constant for a long time. So that is not a problem. Do you agree?
Yes,
Yes,
sir.
sir.
Yes, sir.
Second thing is what? Hold time. What is hold time?
So the minimum amount of time for which it should be stable
After the active age. So after the active age, we can see that the output is immediately charged to VDD, right? So if there is a finite hold time for the non-zero hold time for the flip-flop, this will create a problem. Is that clear? Because hold
Yes.
time, if the flip-flop given to you, it says that it has some 50 picosecond, 100 picosecond hold time. That means the data must be stable for that hold time. After the active age, the data must be stable at that level. But here it is immediately changing. Hold time may create a problem. Is that clear?
Yes, sir.
Especially this will happen if your clock edge itself is sluggish, right? So the clock edge is not having perfect rise time for time, right? It will be sluggish. It will have something like this, something like this. So when the clock edge is sluggish, it may lead to overlap. And in the lecture, I have explained that during the rise time for time of the clock itself, the whole time will be coming, because in that duration, if the input is changing, it may latch to the wrong value. Have you seen? Do you remember that from the lecture?
Yes, sir.
Yes, sir.
Yes, sir.
Because master slave case, you have a master, you have a slave, and you have the clock bar. Is a positive edge trigger. This is clock bar. If the clock and clock bar are having finite rise time for time, during this rise time for time duration, both are transparent. Both of them will be transparent, and both of them will be partially on. As a result, the changing input can propagate, right? So input is changing very quickly, and during the rise time for time duration, it can propagate, and therefore it can lead to false output. Is that clear? So what will you do to solve this? What can be done to solve this?
Sir, can we use a level triggered latch?
Latch we can use, but because you have proposed the flip flop, so is it solvable? Can we still do it? What can be done? Or is not at all
So
usable?
like somehow we have to.
Sorry.
So we will need a higher frequency clock signal.
No.
Sir, we need to ensure that the clock and clock bar are exactly 180-degree out of phase. So, sir, since the clock bar is generated from an inverter, we will be using some inverter to generate the clock bar. So that will introduce some delay. So to generate to use the clock, we can use some transmission gate so that we can artificially introduce some another delay to the clock so that the clock bar and clock are exactly 180-degree out of phase.
No, that will not solve the problem. That is exactly the problem I have drawn here, right? This will happen if it is exactly 180 degree out of phase. Because as soon as clock is going down, clock bar is going up. So that is not going to solve the problem. As soon as the flip-flop's active edge is coming, clock edge is coming, the output is going up. So that will not solve. What will solve?
So
If
we
this
have
is
to
your
add some
comparator,
delay.
if you have the flip-flop, D, Q, and you have the clock, here also you have the clock, what will you do? V in, Vref. Yes. If you delay the clock here a little bit, what will happen? DEL means delay. This is a delay cell. You are delaying the. How can you delay any clock signal? Put two inverters. So if this is the input, output will be slightly shifted by the inverter delay. This is your delay. If this is the clock going to the comparator is slightly delayed, what will happen?
So we will have some hold time.
So now the clock in this case is going to be slightly delayed. The delayed clock. And your clock going to the D flip flop, you are keeping it negative edge triggered. So now that is not delayed. So although it is inverted, but it is not delayed. So its negative edge is going to come here only. So the clock bar is still at that point. Maybe you can use this color. So clock bar is not delayed. It is coming like that only. What is the result of doing this? The active edge of the flip-flop is coming before the clock goes down. So this is clock bar, clock bar. So active edge of the clock bar is coming before the green clock goes down. That means you are getting some hold time, right? So this overlap between the clock and clock bar, because it is active edge of the flip-flop which will decide where the data is recorded, that is coming just or slightly before the clock goes down and the comparator gets pre-charged. Is that clear? You're able to understand? Here it will be delayed, but here it will be, definitely it is inverted, but not delayed. Here it may be, you are putting 2 inverters, you put maybe 4 inverters, you put some extra delay. Here the phase is inverted, but it is lesser delay. Then this condition will appear. Orange, the yellow one is the inverted clock. Green one is the original clock, but delayed with respect to the inverted clock. Is this understandable? The timing of the circuits, wherever clocks are being applied, in many circuits, the timing we need to properly check. What timing will be efficient? Where do we need to insert a delay to make the circuit work properly? So mixed signal circuits, the clock phases, the timing of the clock, etc., the delay matching, etc., putting extra delay wherever required for proper operation of the circuit. That may be important. Is this clear in this case? Yes, anybody, any problem, anything not clear? I'm not hearing any yes, no, whatever. So everybody is clear about this?
Yes, sir.
And
Sir, we can also use that transmission gate, right, to generate a delay.
transmission gate is generally not recommended unless there is a, so in the transmission gate, why it is not recommended? Because it is not directly connected to the supply. So for delay generation, if you have to put some delay in some path, generally we use inverter buffers. So these are called buffer. 2 inverters in series, it is an inverter. So delay generation. So again, the sizes also may not be exactly same. The sizing ratio we will discuss later, but generally in inverter chain, we have, in many cases, we may have unequal sizes. So here we are getting, TIN1, whatever is the delay of the inverter 1 plus inverter 2, as the overall phases are remaining same. Whatever is the phase here, you get the same phase here. Only thing is after some delay. And in certain cases, you may see that cases where people generate differential signal out of single ended. So digital signal. Suppose you have only, one phase clock. You want a single to differential converter. Single to differential converter. Digital, not analog. And at the output, you want clock and clock bar. So how do you do this? So generally, the method used here is that you have in one path, you have 2 inverters. In another path, you have one transmission gate. Transmission gate I'm representing by this switch and then another inverter. And then you have this block. So this is your clock. This 2 inverter will delay it. So it will get clock only. Here it will get inverted clock bar. And we have to make sure that the path delay of these 2 are matching. They are almost same. So for that, if these 2 inverters are identical, we need to make sure that this TG, the switch over here, and the inverter, they are well matched. Their delays are almost similar. But to produce delay, we never use, just to produce only delay, we don't use TGs. We can't use something like this. That if you have just produced clock and clock delayed, we don't use this kind of setup. Let's just use 2 TG and it will delay the clock. Be happy with that. Why we don't use this? Why only inverters? This is a case where this case is only being used to convert the single-ended clock, a single-ended digital signal into differential clock signal. Many circuits will require differential clock. Analog circuits also, there are many circuits will require differential clock. Flip-flops also require clock bar both. So therefore, in many cases, it may happen that your original clock is single-ended and you want to produce differential. Data also, in many cases, we want both the data and data bar. But for the delay production, we don't rely on TG. TG, all of you understand, right? In the lecture, we have discussed TG, transmission gate. This is your, this is your TG, transmission gate. Anybody who doesn't remember or means? So why do we not use this 2 series connected TG? Anybody quickly? Yes. Anyone has an answer? At least somebody should be able to guess.
Sir, is it because of the input impedance that the buffer will have like a very high input impedance?
The digital signal, so we don't talk in terms of input impedance, output impedance. It's not an analog buffer. It's a digital buffer. This thing is a digital buffer. Even number of inverters. So the reason is that if you're having an inverter, it will always connect the output to either VDD or ground. So it has only one transistor coming between VDD and ground. The moment you put a TG after any inverter, the TG does not connect the output directly to VDD or ground. It will connect it to the output of the previous stage. In series, now you are getting 2 transistors, right? So rise time, fall time will be badly affected because it is having an effective R on inserted in series with the inverter. So you are now going to drive an effective, you are inserting an effective R on in series with that inverter. Inverter will directly connect the output to the ground. So only one resistance coming into picture, right? R on the PMOS. But now R out, I would say we can consider this R out of the TG, RTG, R on of TG. And in this case, it is, if it was only inverter, it was only R on of P or R on of N. So now the net resistance total is going to be R on of P or R on of N plus R on of TG. So it is going to increase the series resistance. If you have 2 of them in parallel, it will become this plus 2 times this. 3 of them in series, 3 times this. As a result, overall series resistance will go on increasing and it will destroy your rise time fall time. Is that clear? So for delay production, it does add delay, but along with that, because of this series resistance effect, it will degrade your rise time fall time drastically. So therefore, wherever we have large loads or large number of gates to be driven, we don't use this kind of TG based delay. Always we use inverter. Any question before we proceed further? Yeah. So another way to do this is a latch. Somebody mentioned. So if you use a latch, you can use a NAND latch you have NOR latch or NAND latch. So again, depending on what kind of comparator you have, whether it is a NMOS input comparator or a PMOS input comparator, you can use one of them. So if you use a NAND latch, this is your say S and reset. This is your output Q, and this is your Q bar. This is your NAND latch. So the truth table of the NAND latch, all of you remember? Set, reset, output. What is the truth table? 1 1 0 1 1 0 0 0. What is the truth table? Assuming that this is 1 0 and this is 1 1. What will happen? 1 1 means output will remain 0 0 consistent. 0 1 means output will remain 1 1 consistent. No change, right? So 1 1 means no change. Is that clear?
Yes, sir.
Yes, sir.
0 1. If this is 0 1, it will be Q will be turning 1. Out means Q here. Likewise, this will be 0. 0 0 is an invalid state. So in the case of comparator, which is having NMOS input, this state will never appear, right? 0 0 will never appear because either both the outputs are pre-charged to VDD, one of them is discharged conditionally. This will appear, this will appear, this will appear. And for the pre-charge phase, there is no change. Whatever is the previous state, it will remain as it is. Is that clear? So this can be used for
Yes.
the, NMOS input device. But if you're a PMOS input device, then which one will you use? It will be NOR latch, not the NAND latch. The NOR latch will have just the opposite. Because for the PMOS input device comparator, it will be discharged. Every discharge cycle will be starting from 0 0. Then conditionally, one of them will go high. So we need to make sure that when it is 0 0, state does not change. So it will be NOR latch. So depending on which one you are using, you will use one of them. Is that clear? Any question? But again, this NAND, again, it will be having its own number of transistors, etc. will be bigger. In case you use a dynamic flip-flop that I have described in your lecture, it may be faster also. And in terms of number of transistors, it may be slower. This is also a feasible option. So in digital circuits, some more things that we have, I think, I'm not sure whether it is discussed, but fan out of digital circuits is also, you should know that if you are having one digital gate, which is driving many other digital gates, right? So this is your input clock, and this is, going to many flip-flops. You have a set of flip-flops over here, another set of flip-flops over here. So they are all getting clock signals from these. Likewise, this is going to another. So now we can also, if we assume that this is not present, right? This is not present. And directly I, connect this to all this. What will happen? Suppose, here I have made one inverter. I can make two inverters. So each of them is two inverters.
Load capacitance will increase. Effective load capacitance.
Load capacitance will be more because ultimately what it is driving. So if you look at it, if I assume the dynamic flip-flop circuit that you might have seen is something like this, right? So you will have a inverter, PG, and another inverter. This is one of the flip-flop circuit I might have given or described in that lecture. So this is your D, this is your Q, this can be your Q bar, and you have clock bar, and clock bar clock. This is your dynamic flip-flop. Is this clear? This is dynamic flip-flop. You can add another inverter in, feedback if required. Dynamic flip-flop does not have a feedback. So those things I hope you have covered in that lecture. Everybody understand how does it work? Yes, everybody understand how does it work? Anybody who does not understand? Anybody having problem with this circuit? How does it work as a flip-flop? In this case, if the clock is coming, it is going to, for a single flip-flop, it is going to come here, it is going to come here. Clock bar is going to come here and is going to come here. Eventually, each of these transistors will act as a load capacitor because ultimately the transistors have the gate capacitor, right? CGS, TGD. So effectively, when the clock signal is coming here, you can model this, the effect of this transistor as an equivalent capacitor CL. Therefore, each of these flip-flops are going to load the signal. Effectively, you can model each of them as a load capacitor. And this depends upon the size of these devices because the load capacitor produced by this gate depends upon the gate capacitance, CGS, CGD, etc. Larger is the transistor size, larger is the capacitor. Effectively, if I have to look at the effect of the loading, depending on how many devices are connected, how many circuits are connected, it will have more and more load capacitor. In digital circuits, we will not have load resistor as such because digital circuits will drive the gate of the next gate, next logic or next cell. It will only effectively, ideally, it will provide only the load capacitor. So if your single inverter is driving everyone, then it will face huge load capacitor. And as a result, if before this inverter, if the signal was like this, clock signal was, sharp and well behaved, very less rise time, fall time. After that, it will become very sluggish. Which is not good, right? So we know that if the rise time, fall time is bad, what will happen? Rise time, fall time is bad, what will happen? This
So
is your
it will affect
clock.
the whole time.
Whole time it will affect, and even the rising time is pretty bad, right? So the signal is changing. It will not be very well defined edge. If the edge itself is not there, how will you make an edge triggered circuit? You need to have a proper edge, right? It will trigger anywhere. So if the rise time is very sluggish, it will end up latching anything. You need to have a well defined edge at which the master stage turns on, switches off, and vice versa. So the flip-flop will not work with this kind of bad clock. So we need to have a well-defined edge for edge triggered circuit. And therefore, it will be very important to buffer. You need to have in between, we insert this kind of buffer, say to two inverters. And then now each of these buffers are driving lesser cap. Now, in this case, the load is this divided by 1/3, right? And also the sizes can be increased. If the size of this was W by L, I can make this one say 3W by L. I can make this 9W by L. Generally, the ratio from one inverter to another inverter, provided the load is large. So that is around 3. Again, there is a derivation how this 3 number comes. In Rabe, I will give you a reading assignment. You can look at the derivation. So this number 3 basically gives us optimal delay. And assuming that, how do we calculate the net load capacitor if it is CL? Suppose net load capacitor, all is combined together, if it is CL. Then the gate capacitor of the previous inverter should be at, around at least CL by 3. That way, depending upon CL, we can back calculate and see what is the size of the inverter required. Now, in the simulation, depending upon the capacitor, we can always check that what minimum size of the inverter is giving us proper rise time, fall time. You put if you have a single known CL, large CL whole 1 picofarad. Now, for that, you have to first put ideal signal over here in the single inverter and try to see that with single inverter, what kind of rise time, fall time you are getting. Till you get the desired rise time, fall time, you go on increasing the size of the inverter. And then the inverter before that will be, this is W, this can W by 3. Because if this one turns out to be large, then you can't drive a large inverter using a very small inverter. If this is suppose W by 10, if this was suppose W by 10, what will happen? The signal before the big inverter, that will become bad. Because you can't drive a big inverter with a very small inverter. If this is W, it should be at least W by 3. The previous next one should be at least W by 9, at least. Something like that. So that is called tapered buffer. So this is tapering of buffer, tapered digital buffer. So we maintain a ratio of, depending upon the load capacitor, we find out the driving size or the size of the driving inverter, and previous inverters gradually taper. So that minimum size inverter can drive, the very first stage. This thing also concept should be clear, not only for inverter, any digital gate, NAND gate, NOR gate, any gate. Suppose in a digital logic, you are designing some digital custom logic, you have a lot of gates, NOR gate, NAND gate, XOR gate, whatever. And at some point you see that this particular gate is driving a lot of other gates. This particular gate output is driving many other gates. Then I need to make sure that this gate will be able to handle the load of all these gates. Then I need to appropriately size it up. If any other gate is driving only very few gates, like, this one is driving only one gate, then I don't need to size this one too big. But if one gate is driving too many gates, then I need to size this gate up. So those concepts you should have in mind, so that in case in any circuit you are facing this kind of constraint, when you are designing any state machine or any small controller circuit, there the sizing should be clear. If you're driving a state machine where you have, say, 3-bit state, and you have a logic, digital logic over here, some logic. State machine consists of the static logic and the flip-flop, right? And these are all flip-flop. Ultimately, the output of the flip-flop is going to the, this logic, and the output of this logic is coming to the D, right? D of this. That's what happens. So now, in this logic, whatever logic is being driven, both the cases. First of all, a flip-flop output, if you're driving too many logic gates, we need to have proper buffering. Likewise, logic side, if you're driving, too many flip-flops, there also you need to have proper buffering. So delay point of view, if you see that any point we are getting too much sluggish edge, the rise time fall time is too bad, we need to understand that what is the loading effect. Is that particular gate driving too many gates? Is it too loaded? Right. So those things need to be addressed. Just like in case of analog, we have the analog buffer. In digital, we have this kind of digital buffering. Is that clear to everyone? Any question? This concept is called fan out. So this fan out means a single gate. Fan out means number of equivalent gates being driven. So if it is an inverter, how many similar inverters it is driving? That is fan out. If the inverter size is W by L, if it is driving an inverter which is 4W by L. So although the fan out is 1, in terms of gate, we can say that it is driving only one gate, but equivalent, it is 4 times. So this is W, but in terms of fan out, it will be 4. The fan out in this case is 4. Although it is driving one inverter, but the size of that inverter is 4 times this original size. The number of equivalent gate being driven is 4 actually. So the loading effect has to be taken care. It has to be appropriately sized so that the fan out does not become too big. For any gate, if the fan out becomes too big, the speed will get limited. So this will be especially important if the speed of the circuit is required to be high. For circuits which are very low speed, we may not worry. Circuits which are just having some static signal is not changing frequently, then we may not be too much concerned about the fan out. Fan out will become more critical if you're having a high speed signal path. Any path where your signal speed is very high, there we need to ensure that the fan out ratio is not more than 3 around. Is that clear to everyone? The basic things regarding gate sizing that you should be aware of. Any question?
No, sir.
Okay.
Sir, a
So-
standard CMOS inverter. A standard CMOS inverter will have an input capacitance and an output capacitance both equal to 3C, right? Where C is the standard gate capacitance of any NMOS.
Output capacitance will not be 3C because output input capacitance is built of gate capacitance CGS, output capacitance is CGD, CDB, which are lesser. Is that clear? Generally, CGS is bigger in magnitude as compared to CGD and CDB.
Understood.
This capacitor CGS is generally bigger as compared to CDB, because output side this will come CDB. If it is grounded, it will be only CDB. And other side CGD will come Miller effect you can take. But ultimately, these two caps are smaller as compared to this input side. You are facing this as well as this CGS as well as CGD. CGD will, if you can account for small signal transition point, it will have similar effect.
Yes, sir.
Any other question? So generally inverters, as I mentioned, digital gates or inverter for a given size, the input capacitance will be bigger as compared to the output capacitance in general. Intrinsic capacitance, I am meaning. Output, if you have external device connected or load capacitor connected, then of course that is external. But only the inverter, in output side, the capacitance will generally be lesser than the gate capacitance. And in terms of speed, also basic things should be clear to you. You know, speed point of view, digital circuits. So in this case, inverter versus NAND gate, which one will be faster? In general, suppose your NMOS is same size in both of them, or suppose equivalent. So in general, because when we go for NAND gate or NOR gate, you are having series connected devices, and generally series connected devices means more delay, right? If you have only one device pull up or pull down, then lesser delay. But if you have two devices in the pull down, more delay. So you have to get it equivalent to the inverter, then you have to size it up. So whatever W we have, 2W we have. So here, if you have to get it equivalent, then ideally we have to make it 2W, then 2W, 2W. That part we have discussed earlier. But just as a comparison, you should remember that if for equivalent sizes, the NAND gate will be slower than your inverter. You can also, ideally, theoretically speaking, you can also have 3-input NAND gate, right? So nobody's stopping you. Theoretically, this will also work. But the reason why we don't do it, because this is a 3-input NAND gate. People do use, though, especially if the circuit path is not very fast, we will use 3-input NAND gate. This can be feasible, but then the pull down delay will be longer. If you are using it as for a very high speed signal path, may not be a good idea. Ideally, you can have any number of them. 4-input also possible, but 4-input gates will have longer pull up, pull down time depending upon if a NOR gate, it will be further bad, right? NOR gate is because it is a PMOS in series. You have 3-input NOR gate versus 3-input NAND gate. Now, NOR gate has 3 in PMOS in series. 3 PMOS is even worse as compared to 3 NMOS because mobility of PMOS is smaller. So 3-input NOR gate is even worse. So we have to be aware that in digital circuits, especially custom digital circuits, when you're designing it and combining with analog cells, if we at any place there is a need of 3-input NAND gate, 3-input NOR gate, that will slow down the circuit significantly. Generally, if it is an AND gate, after that you will have an inverter. After this, you will have an inverter. If it is an OR gate or NOR, so generally the inverter does the buffering job. Even after this, if the fall time is sluggish, inverter will sharpen it up, right? Because inverter does the job of buffering. That because just before the inverter, you have this gate which is having a bad pull down because of the NMOS. But just after that, you have an inverter making the AND gate. And for the inverter, there is no, there is only one PMOS, one NMOS. This will transition slightly faster. Generally, inverter can sharpen up the edges. If you give a slightly sluggish edge to the inverter input, it will transition faster and it will give you a sharper output. The inverters can be used to sharpen the outputs. Likewise, these buffers, 2 inverters series can be used to sharpen. So if your input is like this sluggish, after this, it can be sharper. The buffers generally will improve the rising fall time, especially if they're properly sized. So these basic things you should know that when you're designing any transistor level circuits, what happens to the rise and fall time, what happens to the your delay, etc., and how to take care of loading effect in digital circuits that you should be aware of. Generally, when you synthesize big digital blocks, this sizing, etc., is taken care by the synthesis tool itself for the digital synthesis when you're designing the digital circuits using Verilog. But custom analog circuits will also require digital blocks, digital cells, AND gate, NOR gate, flip-flops, latches, anything. So in that case, you have to design using transistors. And for that, you should be aware of all these delays, all these issues of sizing, loading, etc. Any question before we proceed further? I will also take a test very soon for the first phase so that I know that till now how much has been absorbed by people. I can see that the attendance is now further down from 30, it has become 20. So we are converging. Yes, any question before we conclude, before we proceed further? So this comparator assignment, I think you should be able to do easily after all this discussion. And this sizing, etc. Anyway, these are basic things you should remember. Let me think whether anything else I can cover. CMOS scaling we have not covered, so scaling is another thing that we should cover briefly. That will require some time. Or analog side, we can cover some more things. Sample load circuit you have covered. We will cover some more advanced sampling circuits. Let me see.
Excuse me.
Yes.
Sir, one doubt which I had was regarding that generating the sampling clock. So in your lecture, you said that we will use a counter and then we can perform an AND of Q1 bar, Q2 bar, and then up to Qn bar and clock bar, which will give me basically the sampling clock. But since we're using ripple counter, in the ripple counters, we'll be having delays between every Q1 and Q2, right? So that will result in glitches in between the sampling clocks. So, sir, how can we deal with that?
So that delay can be done, adjusted by the, buffers, right? You can add whichever path has less delay, you can add that much of buffering.
Okay, sir.
Generally, delay matching can be done if you're using a ripple counter. From the input to the output, there is some delay because here you have a ripple counter. Output of this one is going to the clock of this, clock of this, clock of this. So as compared to the input, the output will be, this is the highest frequency clock to the input. And then, gradually it will have some delay. So the final clock that you're getting, it will be coming after some delay. This delay. Now, if you want to replicate, we need to add this much delay to the, if you want to have delay matching, then we need to insert some buffer which takes care of this much delay. Right. So in the path of the previous block, you can add some delay so that it compensates. That's all. Is that clear?
Yes, sir. Yes, sir. Yes, sir.
Synchronous counter will be, of course, more clock synchronized because all the flip-flops will change their state at the same location, but that requires state machine. So you need to have a state machine based counter. Here the benefit is that power consumption is lower because this is operating at F, this is operating at F by 2, this is operating at F by 4, this is operating at F by 8. Synchronous counter every cycle, clock is coming. So that will be more power hungry in general. So here it is power P, this will consume approximately P by 2, P by 4, P by 8. So, but if it is a synchronous counter, generally the power consumption will be almost equal to the number of flip-flop. So synchronous counter is okay if your total delay is not so bad, so if it is becoming comparable to half the period, then it is bad. Then we cannot use it. So we need to make sure that the delay overall for the ripple counter is not too long, that it becomes comparable to the period of the signal or the sampling period. This is the sampling period. So T sample. Any other question? Okay, so today I don't think there is a lot of assignment material. Already I have given you comparator. I can, unless I teach something else, I will not be able to give you an assignment. Second assignment, comparator, you can always add the latch and you can complete that comparator. That is possible. Resolution of both the comparators you can determine. Speed you can determine. How many have maybe the dynamic comparator I did not discuss, so you people have not done that resolution analysis. Theory point of view, maybe a few more things I can cover. Let me think about it quickly. What exactly should I cover in half an hour? Kind of scaling. Let me try. It will take some time, but it's okay. So CMOS scaling, you people, the EC people might have studied, right? So how many E people are remaining? All of them have fled or still remaining? Let me see. E people, how many? Only 2 E people. 3. Okay. So 4 E people. Okay. Rest have fled. Okay. So let's see. I will have to see how many people are performing in the test. After that, only I will, restrict to those many people. So the question was, should I continue with something further? So maybe rather than going to scaling, I can, those who have already completed the comparator, I can give you some more design, a simple component, because you have done the op-amp. So you can design amplifier, you have seen, comparator you have seen. So both are important parts of the analog circuits, amplifier as well as comparator. In the ADC design also you have seen comparator is being used. Comparator, there is another part called offset cancellation that you have not covered, but I can ask you to read that lecture so that you can understand at least what is the complexity with the offset cancellation. So another application of the op-amp, apart from amplification, right? We have already seen amplifier using op-amp. So another application is LDO for power management, low dropout regulator, low dropout regulator. So the purpose of this is to provide a clean output voltage. And there are several ways in which we can make it, but I'm going to give you simple topology and ask you to maybe simulate and try to see what is the issue coming, whether you are able to get it. There can be, the low dropout regulator is generally conventionally used to provide a stable DC voltage to the loads, to the other circuits, other components in the chip. So this can be on chip, or it can have basically integrated or discrete. Integrated means you have a board, a PCB in which there is an LDO chip, and you're taking the DC voltage from some source and providing it to some other chip, maybe ADC chip. You need, say, 1 volt. You're getting, say, 2 volt from somewhere, which is noisy. You want exactly 1 volt clean signal to the ADC. You're doing it using an LDO. And there is another, this is your off chip, or basically, I would say discrete LDO. And in many mixed signal systems, you will require on chip LDO. That means the same chip, you should need to have an LDO on the same device, because then you don't need to have separate LDO for different components, or you don't need to have a separate LDO outside the chip. So that is integrated LDO. So a simple way of doing the LDO is basically you can have 2 options. One option I'm drawing here is a PMOS, which is taking the external supply, which is noisy. And then you have effective load capacitance over here, CL. You can also have some effective load resistance, RL. Suppose the RL is very large. Digital circuits, generally you can model RL, but assume that RL is very large, you're ignoring it. You're having some load current, IL. IL is some effective load current, depending upon how much load the circuit is taking. It can change over time, especially if the digital circuits are there, it can change over time. Analog circuits, the bias current is generally fixed. So if it is catering only to analog circuits, generally it may have some constant profile. But for digital circuits or mixed signal circuits, where both digital and analog are together, there this IL may change over time. And then I need a constant voltage over here. This V out should be constant because this is a load. This is your circuit. Whatever load you are having, it may have many components, ADC, amplifier, it may have filters, whatever. So plus some logic. So all these things are within this circuit and they're taking an average IL. Some over the time it is taking some average IL. It is not exactly constant, but average IL. And then I want this V out should be very precisely controlled. This should not vary by more than 1 millivolt. So peak to peak, 1 millivolt precision. This one is having pretty large, maybe 20 millivolt precision, millivolt swing. So now I need to have this one as constant. So now I can use an op-amp. I can use a reference voltage for this so that, this signal V out is equal to Vf, and I can use a negative feedback so that my output voltage is close to the Vref. Or I can also use a voltage. Generally, there will be a voltage divider used over here, R1, R2, and I put this divided voltage, V mid, to the feedback over here. Now, the question is, what should be the polarity? Whether I should connect the VM, why we have put this voltage divider, I will come to that. But before that, whether I should connect the VM to the positive terminal of the op-amp or negative terminal of the op-amp for negative feedback. Op-amp job is that these two voltages will try to make sure that they are very close. So if this is very close, then definitely we can make sure that the VM, VM is just a divided version of V out. So VM is very close to Vref. In other words, V out is also close to the desired value. So whether it should be positive or negative terminal?
Positive, sir.
Positive. Why positive? Because if this is a reference and this voltage, suppose because of some reason, the output voltage is increasing, what will happen? If it's a positive terminal, output voltage here will also increase. Op-amp output will also increase. That means the current produced by the PMOS will reduce because the VG is increasing. And as a result, this output will go down. This output will go down, this will go down. That means it is having negative effect. It is cancelling the initial assumed change. Is that clear? Is that clear to everyone?
Yes, sir.
Yes. Hello?
Yes, sir.
So this is a simple low dropout regulator. Why we call it low dropout? Because in this case, the dropout voltage across the PMOS, we try to keep it low. That means the VDS, we try to keep it low. Now, in this case, we can also have another alternate version where we replace the PMOS by an NMOS. If I replace the PMOS by an NMOS, what is the benefit? What is the disadvantage? If you replace it by an NMOS, what will happen? Is the same connection going to work or something going to change?
VM will be at negative.
Negative because now the NMOS will work like a source follower. It will not have phase change between the gate and the source. PMOS in this case is working like a common source because source is at the external, whatever DC voltage you are putting over here. So this is going to lead to a phase change. From here to here, there is a phase change. For NMOS, if you put gate to source, it is like a follower, voltage follower kind of common drain kind of structure. So therefore, this polarity has to change. Is that clear to everyone? What else will change? The purpose of the LDO is to reject the noise. If there is a noise at the external DC, it should reject. You should not pass that noise to the output, V out. Which one will be able to reject it better, NMOS or PMOS? Fast. Quickly. This should be very simple. Which one will be able to suppress the noise passing from the, sorry,
NMOS.
NMOS will do it better or worse? Like it will pass the noise or not pass the noise?
It will
Or pass
not,
the noise less? Why?
because it is very low signal, so it will turn off.
Sorry,
Due to low signal, it will turn off.
what do you mean turn on? This is not the right answer. Anybody else?
It has something to do with the mobility of holes. Because
No,
of that, it has.
no.
Okay.
Anybody else? Anybody else? Simple things.
Sir, in NMOS, it will work in common drain, like uh, it will work as a common drain amplifier, and in PMOS, it will work as a common source. So, will that one be the reason?
Common drain. So for a signal at the drain, it will work as a common drain. Where is the noise coming? Noise is coming at the drain. So if it is an NMOS, the noise is coming here. Will it pass to the source? The conductance from drain to source is less, right? So you can keep changing the drain voltage. It will not affect the current so much, and it will not affect the voltage so much. Right? But if it is a PMOS, you are changing the gate to source voltage. So the PMOS, it must the op-amp must compensate so that the VGS remains exactly same. Otherwise, it will drastically change the. It will pass the noise to the output. Is that clear? So here the op-amp has to do
Yes.
more job. It has to operate fast and cancel the noise. The moment the signal goes up, it has to follow and get the gate voltage again up so that the VGS gets cancelled. And if the noise is high frequency, op-amp may not be able to track it fast. Then the whole noise will pass to the output. For NMOS, that problem is much less because it's a drain signal changing. VGS is anyway remaining well controlled. Is that clear? The PMOS will have more noise passing from the input source to the supply, the controlled output V out. Whereas NMOS will have lesser. This is called power supply rejection, PSR. PSR. PSR of NMOS will be greater than PMOS. Is that clear? But then still why people may use PMOS? Many cases PMOS is used. Why? Because the dropout. So in which case the dropout, that means this difference in the external voltage and the output voltage will be more. Yes. Tell me fast. No answer means what is going on? Basic things you're not able to say. This difference between the input voltage and output voltage, which case it will be more, PMOS case or NMOS case?
The PMOS.
Remember that this op-amp is also working with some supply. Suppose it is working with the external supply, whatever is the external voltage, not very clean, but it is working with that supply. Then in which case the output voltage drops from the DC, the maximum voltage that you can have here at the output, which case it will be more.
PMOS.
PMOS, right? Because now the op-amp is working with, suppose your external supply, suppose it is 2 volt, right? So this is working with 2 volt. So output maximum it can go is up to maybe, in this case it is 2.22 something, it needs to have some VSG drop. So suppose it needs to have the VSG drop of the PMOS. So the gate point, it will be 2 minus VT. suppose something like 1.5 volt. So the drain voltage, while keeping the PMOS in saturation, the drain voltage can go all the way up to what? VG plus mod VT, right? That means back close to 2 volt. So in case of PMOS, this drain voltage can go to VG plus mod VT, T, right? So it can go as close to 2 volt. That means the VSD drop can be low. Whereas for NMOS, if it is driving in NMOS, so for NMOS, it always requires this VGS drop. Even if the gate voltage is completely driven to 2 volt, we will have a VGS drop. And that is greater than VT, right? So the NMOS will have bigger drop. So therefore, for a given external voltage, the maximum output Vout that you can have will be more in case of PMOS, less in case of NMOS. Is that clear? So dropout,
Yes.
dropout, you will have also NMOS greater than PMOS. Now, power supply rejection, NMOS greater than PMOS is good. It is a happy case, but this is a bad case, right? So PSR, NMOS will provide better, but the dropout, NMOS will be worse. And what does that mean? Like why do we worry about lower dropout? Because it is something related to efficiency. Efficiency means whatever is the input power versus output power. So P out versus P in. What is the input power to the LDO? That is, suppose this is VDD external times the I load divided by P in. What is the actual power delivered to the circuit? This is V out, whatever is the internal VDD times I load. This also has additional component, which is because this op-amp and this will also require some bias current. So it may have some IQ, whatever is the bias current required to operate op-amp, because this is different from IL. IL is going to the load, but there is some bias current IQ which is required to operate this op-amp. So that IQ into VDD external will also be there. But assuming that that part is small, I'm ignoring it. The efficiency will ultimately depend upon V out external and V out. Right? If these are close enough, the efficiency is bigger. Otherwise, there is power loss. We are losing power. So especially for battery management or low power system, we would like to minimize this power loss. Therefore, having a bigger dropout is a disadvantage. We are losing power. We are wasting power. Is that clear to everyone? Any question on this? Any question on this?
No, sir.
Now, there are many design parameters in this that will decide the overall operation of the circuit. First thing is, so what are the design parameters you can think of? So I will not complete the whole thing. It will take a lot of time to describe the whole thing. But what are the design parameters you can think of? One is design specification and another is design parameter. So first thing is design specification. What are the design specifications? Just like for the amplifier, we have some specifications depending on the input signal. Here also we have some design specifications. What are those design specifications that come to your mind? Quickly, fast. Already we have discussed a couple of them, right? So they are also design specification, PSR, efficiency. These are two design specification. What else? Power supply rejection will tell you that, okay, what is the ripple it can tolerate? What is the input supply ripple it can tolerate? Despite having a noisy input supply from outside chip, how clean supply it can provide to the circuits on the chip. Efficiency will tell you how much power it is losing. With me, how much power it is losing. What else? Quickly.
Fan out.
Sorry?
Fan out.
fan out. You said fan out. Fan out is a digital thing for digital circuits. How does fan out come here? You can talk about IL, what is the load current it is supposed to supply. There will be some range, right? Whether it is, 10 microampere maximum IL max, whether it is 1 milliampere, whether it is 100 milliampere, right? So what is the value of IL max? What else? What else? IQ is also a parameter. How much static current you are burning, how much current you are wasting in the op-amp. So very high efficiency LDOs, we would like to minimize the IQ, the biasing current in the op-amp, so that the power wasted in the op-amp is lesser. What else? There is something called response time. That means if your input signal, input means your VDD, or in case your load current, IL is having a jump, right? IL is going from Imin to Imax. So your IL is going from Imin to Imax. This is your IL going from 0 to Imax. Or 0, it can be some Imin also, not necessarily 0. So how quickly your output voltage will settle back to the required value? Because whenever there is a change, sudden change in the load current, output will drop, and then finally it will, try to settle to the required value. So this is your V out. So if there is a sudden change in the load current, the output will fluctuate. It will, have a jump, and then it will try to settle back. The op-amp will not, it is not an ideal op-amp, right? It is not an instantaneous op-amp. It will have its delay. Op-amp loop, right? Ultimately, op-amp is regulating it, right? So op-amp has limited bandwidth, and in this loop, there is a finite delay. So if there is a sudden change in IL, what will happen? It will completely pull the output voltage down, because there is a net load capacitance over here. It is storing some charge. But if there is a sudden jump in IL, it will try to discharge this capacitor, bring the V out down. Now, the op-amp will take some time to respond and then settle the gate voltage to a new value, so that it can change back. That will take some finite amount of time. So that settling time is important. That is the response time or settling time. Right? That is how it is calculated. What else will be the specification? Anything else? There are two important terms: line regulation. Line regulation means that if your the V in is changed, your V in is changed. Suppose on x-axis you are changing the V in, and in V external. V out, how much does it change? Does it the V in change in, say, 2 volt to 2.5 volt? How much the V out is changing? Is it changing by 10 millivolt? Is it changing by 100 millivolt? What is that change? That is called delta V out by delta V in. Delta V out by delta V in. For an ideal LDO, delta V out should be 0. It should be exactly able to maintain whatever is required. But in a real case, it will be having some change. That is called line regulation. And there is another similar term called load regulation. Load regulation means x-axis you are changing the load current IL. For a given V in, you are changing the load current IL. So as you increase the load current, what should happen to V out? It will go down. So as compared to ideal value V out, when you change the load current from some 0 to IL max, this slope, like how much is the delta V out by delta V in, delta IL, that is the load regulation. So again, for an ideal LDO, we would like this drop to be minimum, right? So that is the ideal case. But again, in real scenario, it will be having this kind of drop. So all these parameters, all these design specifications will depend upon the design parameters that you are using. These are design specifications. This will lead you to design parameters, whatever design parameters you are going to have. So how will you, what are the design parameters in your hand, roughly speaking? Design parameters. Yes, anybody? I hope it is understandable, right? I'm speaking. I hope I'm going at a proper speed. Anybody not getting? What are the design parameters?
So the op-amp gain,
Sorry,
the gain of the op-amp.
op-amp gain. Op-amp. Again, gain A naught, bandwidth. Bandwidth will also be there. What else? Yes. What else? What is another important parameter that you can see in this, which is going to affect some of these specifications?
So load capacity.
Okay, so load capacitance can be given, but generally for designs, people can put some desired capacitance. So you can have a design, added capacitance. So load capacitance can be given that in this circuit, this is the net load capacitance. But in order to meet certain, parameters, you can put a load capacitance, additional capacitance. What is that parameter? I have not mentioned that specification, but what is that? Phase margin, right? The feedback circuit, you need to meet a certain phase margin. And we have discussed some compensation scheme. So in many cases, you may need to compensate. You need to have a proper phase margin. For that, you may need to add additional load capacitance. So CL may be a parameter. You are provided you are putting some additional cap for stability. What else? Pass transistor. That means PMOS or NMOS.
Size ratios.
Because if the pass transistor is very big, it will be able to support bigger current, right? If the pass transistor is small, it will not be able to support big current. That should be obvious, right? Is that clear? If you have to support big current, 100 milliampere, definitely you will need bigger pass transistor. That means this one, that is also called power MOSFET. Whatever is the MOSFET supplying the main current, this guy. This is your, generally we call it either pass transistor or the power MOSFET, which is supposed to supply the power. So in this case, this pass transistor, if your transistor is big, it will be able to support bigger IL. If it is small, it will be able to support smaller IL. The size of this MOSFET depends upon the load current specification. If the load current is big, we need to make it big. Any other thing that you see? Anything else? So now the question is, there are two cases. Suppose we are going for, say, the PMOS case, or the PMOS load transistor, or sorry, the PMOS pass transistor. So there, what are the critical nodes that you see? What are the sensitive in terms of high frequency poles? What are the sensitive nodes for stability concern?
Sir,
Yes,
the
fast.
V out node. The V out node.
V out and generally this R1, R2, we keep it very high so that the power is not wasted, because R1, R2 will contribute to IQ, right? So IQ, that static current which flows in this remaining circuit. IL is only going to the load, but remaining current which goes to this voltage divider and the current which is consumed by the op-amp, that we want to minimize. So for that reason, R1, R2 are anyway kept very big. So
VM
what
node
are the
also.
critical nodes?
The VM node,
Gate
the point where
V in point.
the VM.
This point.
VM.
VM, yes.
Sir,
VM, this VM. VM generally, yeah, so generally the input devices are not that big. So as compared to the load that you are seeing here, because this load capacitor is big because this pass transistor is big, much bigger. So generally, we will not have this much as a critical pole. This one will be much bigger, the gate capacitance, because this pass transistor is very big as compared to the MOSFETs in the op-amp. So in general, we will not consider this VM pole, to be very close to the or very, sensitive. Output side, if it is a PMOS, then definitely your impedance is RO. RL, we have anyway assumed that it is large. R1, R2 is large. So digital circuits, we are assuming that there is some CL and there is some load current IL. And there, here the net, impedance will be given by the MOSFET. Now, if the MOSFET is very large and the IL is also large, in that case, the impedance will be lesser, right? Because 1 upon lambda ID. If the ID is big, you are going to have lesser impedance. RO will be lesser. But if the current reduces, because LDO's purpose is to maintain the V out same, irrespective of the IL. IL may change depending on the load circuit. Sometimes it may be very low, close to 0. Sometimes it may be close to IL max. So this node will become more critical at what point? IL max or IL min? Yes, fast. Yes, can you answer fast?
Sir, IL max, right? Because then the resistance of the NMOS, the fast transistor will be lower.
Then the impedance here will go down, right? So then it is no more critical pole. When the current is very small, then the RO of this guy will be very large, and as a result, it will form a low frequency pole, much lower frequency pole. When the current is maximum, then anyway the RO is lesser, right? And then it will not have a critical pole. It will push the pole towards high frequency. So dominant pole will come at this node if the current is low. IL is towards lower value. So the output pole is, we see it is changing depending upon load current. Right? So output pole can keep changing depending upon load current. That can be problematic. In the op-amp circuit that we saw earlier, we had a fixed pole. But in LDO, this node, the pole can keep changing. That can create problem, right? You have to stabilize it for the worst case scenario. Worst case scenario will appear when the current is minimum, because there, this is also critical node, this is also critical node. Op-amp output, especially if you're not buffering the output, if it is an unbuffered op-amp, then this will also create a critical pole. This node will also create a critical pole. VG will also, this gate voltage will also create a critical pole. VR will also create a critical pole for low current. So in that case, the phase margin has to be set such that for the minimum current, the phase margin is satisfied. This pole is not creating problem. If you buffer the op-amp, then this pole will probably go towards higher frequency, because now if a buffered op-amp, then it is not driving a big cap. It is not driving a big gate capacitor directly using a high impedance state. If it's a buffered op-amp, common drain buffer, whatever you are including, then it will be driving through a low impedance state. Then this pole will be towards higher frequency. And then this will remain the critical pole, because then this towards the low current values, it will become dominant. But now if you buffer it and when the current increases, this will also shift towards high frequency, because now you have buffered the op-amp. This pole has gone towards high frequency op-amp output. But now when the IL becomes high, then this impedance will become again low. This will also go towards high frequency. So both the cases, the problem will come. You understand this point? Yes, is this clear to you?
Sir, can you repeat once the last point that about the IL going high?
Case 1, where you have not buffered the op-amp output is a high impedance. and they are driving that PMOS, big PMOS with that op-amp, then that is also providing critical pole, low frequency pole. In that case, the output will become critical when the current is reduced, lower load current. In that case, output impedance is high and the pole is going towards low frequency and it may become close to the op-amp output pole. Then it will create instability. Is that clear?
Yes, sir.
And second case, you buffer the op-amp. That means after that you could put a common drain stage. Then what happens? If it is a buffered stage, then the pole at the buffer output becomes high frequency pole because that is a very low impedance buffer. But now the IL, if the IL becomes high, then it will also become high frequency pole. Again, it will create problem. Is that clear?
Yes, sir.
So in one case, you will get problem with low current IL. In another case, you will get problem with high current IL. Low current IL will be problematic when you have unbuffered op-amp because lower current will, push this output pole towards low frequency. It will start coinciding with the op-amp pole. Buffered op-amp will have poles towards higher frequency for the op-amp, but if in this case load current becomes high, then it will push the output pole towards high frequency. Again, it may become close to the op-amp pole. So both these cases will become problematic. So low IL will be problematic for unbuffered op-amp, and high IL may become problematic for high IL may become problematic for buffered op-amp. Is that clear? So for both these cases, we need to make sure that for the entire range of IL, we are getting stable behavior. So we need to compensate for the entire range of IL. That is the main problem with the op-amp as compared to standalone amplifier. Op-amp has a varying pole. Is that clear to everyone?
Yes, sir.
Yes, sir.
If you put an NMOS transistor, then again similar thing will come, but the output impedance is low because of the NMOS. But still, if the load current is low, the output pole can shift towards low frequency because 1 upon GM will be low. The GM will be low. So again, this thing will be discussing in more detail maybe tomorrow. And based on this discussion, you can always for a small. Why are we putting a voltage divider here? R1, R2. Why not directly connect this drain to the input of the op-amp? Yes. Any answer? Yes. Any answer?
Sir, that V out pole, the V out point node will see an extremely high impedance, right? If we directly short it to the positive terminal. So
What do you mean? R1, R2 is already very high. So how does it matter? R1, R2 is much higher than the RO of the MOSFET. So it is not mattering. Yes. Anybody else? Not getting good answers.
RL be shorted.
Forget about RL. RL doesn't exist. I told you it is very high. What do you mean by shorted? RL will get shorted if you connect directly to the op-amp input. Yes. Any problem? Op-amp will have some problem. I gave you half the answer. Now tell me what problem. Yes. What problem the op-amp will face if you directly connect the output to the input of the op-amp? Oof. this should be answerable. I don't know what is going on. Yes, anybody?
When
and
V out
it's
will be Vref equal to Vref, then it will fluctuate.
How will it fluctuate? What is the logic behind the fluctuation?
Both will be exactly equal.
Then what is the problem? Could be, the answer should be reasonable.
so there will be a 180-degree phase shift between the output and the input if we directly connect the output with the
Input is here. So
no, sir. The op-amp output and op-amp input.
op-amp output and op-amp input. The positive output of the op-amp is connected to the PMOS. Then what is the problem? Negative feedback is present, right? Whatever be the case. Yes, anybody else? This has to do something with the input common mode range. Not tell me the answer. 80% I have given, or maybe 90%. 10% you can tell me.
The common mode values of the output and the input may not match.
Sorry? Yes, louder.
That the common mode values of the output and the input may not be same.
I said input common mode range. Still you
So
are not
for
catching the answer.
For a delta V fluctuation at V out, the same fluctuation common mode range will be R1 by R1 plus R2 into delta V. So
Forget about
that
R1,
will-
R2, it is not existing. I'm talking about the case where you're directly connecting the V out to the positive input. Your op-amp has some finite input common mode range, right? So if your output is close to VDD, V out and VDD, we are trying to make it close, right? V out, and in this case of PMOS, especially the V out is going to have a value which is close to the supply. And then the op-amp is also having that same supply, suppose. Now, if you connect the input also, to the same value, what will happen? The condition for the transistors, if you have a op-amp, you are having, the supply is suppose VDD external, and then you are, directly this whatever is your output, feeding it directly over here. This is VDD external minus some delta V out. And now this Vref is also going to be very close to this. That means if it is say 1.2 volt, you are going to have say 1.1 volt over here, 1.1 volt over here. Vref also has to be 1.1 volt. So you are trying to operate this amplifier with 1.1 volt. What will happen? If this is the NMOS device, op-amp, 1.1 volt, VDD 1.1 volt, what will happen? What will happen? Yes, tell me. Input common mode range, right? So maximum value this transistor may enter into triode, right? So because this is 1.1.1 volt minus VGS, maybe 1 point something, 1 point from 1.2 volts. Suppose this was I had kept 1.1. So this was 1.1, and suppose this is VGS. So maybe 0.8, something like that. And then you are trying to give this very high. So these transistors will operate close to triode region because the gate voltage is too high. This is almost at the verge of triode. So for the maximum voltage, the gate voltage is too high. For the op-amp input stage, the main devices will be close to triode region. Because whatever you assume that the VT is 0.3 volt. So here you will get higher than 0.3 volt drop. This will be 0.8, lower than 0.8. As a result, this drain voltage will be lower than gate voltage by 0.8. As a result, the input devices will be in triode. Gain will be poor. Is that understandable? Therefore, we would like to bring them down, the DC level feedback to the op-amp, bring it down to voltage divider and bring it down to maybe VDD by 2, keep it around 0.8 volt, 0.8 volt reference. If you use the voltage divider, and then you can keep the reference also low, so that the reference value is close to mid value, VDD by 2. Is that clear? Is that clear to everyone?
Yes, sir.
Like this thing we have discussed, but answers are not coming. So let us conclude for today. Maybe based on this, I can give you some additional small assignment. But first, finish the dynamic comparator one. LDU, I will give you some small steps to at least start with. Any question before we conclude? Any question before we conclude? And how many people understood everything that was covered today? How many people understood everything?